identification and tracking of unmanned aerial vehicles based on radar data. Problem statement. The problem of effective counteraction to the illegal use of UAVs has become particularly relevant. After all, the drone industry is actively developing, but there is no universal method of combating it. The relative accessibility and ease of use of drones make them a convenient tool and potential target for illegal abuse. Therefore, the aim of our work is to develop an algorithm to solve the problem of correct identification and tracking of UAVs based on data obtained from radars and sensors. Literature review. We have analyzed the most relevant research on this topic. Here is a summary of the main information. The fight against the illegal use of drones is divided into two stages: tracking and neutralization. There are four main means of detection: radar, acoustic, optical, and radio frequency, but each of them has significant drawbacks. To eliminate them, integrated systems are used. In addition, significant progress has been made in image processing and computer vision over the past decade. Modern technologies make it possible to detect objects in a video stream and in image, as well as to classify them. These technologies can potentially be used in this task. Therefore, the research task in this paper is to develop an algorithm and design an automated system to solve the problem of tracking and identifying drones based on data from radars and photo or video cameras. The developed software should process this radar data and analyze images using artificial intelligence. Input and output data. As mentioned before, input data sources are radar measurements and the image provided by the camera. Since this information arrives simultaneously and needs immediate processing, we consider the stages parallel in the proposed algorithm. The input data are the spatial coordinates and speed of the observed object, which are received from the radar with a certain frequency, as well as the image received from the camera, which is presented in the form of two-dimensional array of RGB vectors. The data coming from the radar has some noise, therefore for their further use is necessary to localize this trajectory to bring them closer to the real indicators. Images are analyzed by AI methods to obtain useful information within the defined task. In this study is classification for object identification. Therefore, the output data of proposed system are localized spatial coordinates and information about the type of observed object. Proposed algorithm. The tracking procedure can be described as an iterative process. Probing by the locator occurs with a certain frequency, so we will consider each radar cycle an iteration. Data is sent from the radar to the system at each iteration. They are transferred to the system component responsible for their processing, namely localization. In parallel with this, an image of the observed sector, which contains the detected object, is received from the camera. It is proposed to use Kalman filter to solve the localization problem. Object identification within this work framework is reduced to a binary classification of the input image using convolutional neural networks. For practical use, CNN requires a preliminary training stage. The development of the classification module starts with the training of the model. Since this work solves the problem of binary classification of images, therefore the dataset for training consists of two classes of images, drones and birds. You can see the architecture of the neural network in the image on the right. Experiments and results. First, let's look at the task of localization. The localization task includes two stages. The first is data generation. We generate a dataset that would simulate the measurements of the locator. We took the file of drone flight logs. The flight logs contain time-sampled geographic coordinates of the drone throughout the entire flight trajectory. Then noise was added to this data to simulate the radar measurement error. The second stage is applying the Kalman filter to the generated data and measuring the errors to evaluate the results. For each file, total 3, with noisy radar measurements, we will find the root mean square error relative to the true trajectory. We will perform the same operation for the localized data, which will allow for further comparison in the before-after format. The result of the calculation are shown in Table 1. Then the model was trained and its accuracy was evaluated. The estimates of class prediction by several metrics are shown in Table 2. These slides visualize how the system works. To do this, we generated a fragment that simulates radar measurements when a drone is detected, and also took several frames for drone flight video as data coming from the camera. Conclusions. The developed system can serve as a starting point for creating a full-fledged tool to counteract the misuse of drones. The main direction for further research are solving the problem of tracking and identifying several objects in the monitored sector simultaneously, modernization of the classifier to identify the type or model of the detected drone. Thank you for your attention.